So, History of Mathematics, Lecture 26. And it's the last class. We have the final exam on Monday at 8:30 in the morning, Gillette Hall, room 205.
Professor, can we do problem 6 from the final?
Problem 6 from the review sheet?
Yes.
Okay, sure. So review problem 6 is to define rational, algebraic, and transcendental numbers. So a rational number is a fraction. That is a number of the form P over Q, where P and Q are integers, and the denominator is not 0. So 2/3 minus 17 over 5,000, 21 over 3. These are all rational numbers. And they're rational numbers whether or not they're reduced to lowest terms, just a quotient of integers. So that's what a rational number is. And you can observe that every rational number, P over Q, is a solution of the linear equation, Qx minus P equals 0. So if you take this equation in X, this is linear, it's first degree. And if you let X equal P over Q, you get 0. So every rational number is a solution of a linear equation with integer coefficients. The coefficients are P and Q. And an algebraic number is any number that is a solution of a polynomial equation of any degree with integer coefficients. So for example, if you take the polynomial x squared minus 2 equals 0, what are the solutions? Square root of 2 and minus the square root of 2. Right, so if we write this as f of x, then f of the square root of 2 is the square root of 2 squared minus 2 is 2 minus 2, or 0. So these are both, and the same with minus. So these are algebraic numbers. If you take f of x equal x squared plus 1, what is the solution? Well, f of I is I squared plus 1. I squared is minus 1 plus 1 is 0. So the complex number I, so these are algebraic. And so I is algebraic. And so on. If you take the equation f of x equals x cubed minus 1, what are this is a polynomial of degree 3. What are the solutions? You can have f of 1 is 1 cubed minus 1 is 1 minus 1 equals 0. So 1 is a solution. And sorry, let's make this x squared. No, sorry, x cubed. X cubed. Yeah. What else is a solution? If you take minus a half plus root 3 over 2i, that's minus a half plus root 3 over 2i cubed minus 1. Let's see, what is that? If you cube this, you get minus a half cubed plus 3 times minus a half squared times root 3 over 2i plus 3 times minus a half root 3 over 2i squared plus root 3 over 2i cubed minus 1. So if you cube minus a half, you get minus an eighth. What is this? Minus a half squared is 3/4. 3/4 times root 3 over 2i. I have 3 times minus a half, that's minus 3/2. If I square root 3 over 2i, I get 3 over 4 times minus 1. Root 3 over 2 cubed is 3 root 3 over 8. I cubed is minus I minus 1. Let's see if I'm lucky enough and this works out. This is minus an eighth plus 3/8 root 3i plus 9/8 minus 3 root 3 over 8i minus 1. Minus an eighth plus 9/8 is 1, minus 1 is 0. 3 over 8 root 3i minus 3 over 8 root 3i is 0. This is 0. Yeah. So if you just do arithmetic, and so by the time you get to 300 level math class, you should certainly know how to add and subtract and multiply complex numbers. This is 0. So this number is an algebraic number. So an algebraic number is the root of a polynomial equation with integer coefficients. And a transcendental number is a number that transcends algebra, is simply a number that is not algebraic. And to prove a number is transcendental is always very difficult. But two examples that you know and love are pi and e. So if you look at all the numbers, all the complex numbers, you have the algebraic numbers and the numbers that are not algebraic, which are transcendental. And sitting inside the algebraic numbers are the rational numbers. So that's the definition. And for an example, this is part B. Suppose we let gamma be root 5 minus 1 over 2, which, if you know a little bit of geometry, is the golden mean. And we want to prove this is irrational, first of all. So if gamma, it's a proof by contradiction, if gamma is rational, then gamma, which is root 5 minus 1 over 2, is p over q for some integers p and q, p, q integers. Right? If the number is rational, it's a fraction. So square root of 5 minus 1 is 2p over q. So square root of 5 is 1 plus 2p over q, which is 2p plus q over q. It's a fraction. Let me just write this as r over q. So if gamma is rational, then square root of 5 is rational. And if you square both sides, 5 is p over q squared, which is p squared over q squared. So, and we can write, sorry, this is r over q. And I can write it so r and q are relatively prime. You can write every fraction in lowest terms. So r and q have no common divisor. So if I square root 5 equals r over q, I get 5 is r squared over q squared. So 5q squared equals r squared. And now we just continue exactly the way we proved square root of 2 is irrational. So this means 5 divides r squared, which means 5 has to divide r. If 5 doesn't divide r, it doesn't divide r squared, because every number is, can write as a product of primes. So I can write r as 5 times s for some integer s. So if I plug this into this equation, 5q squared is r squared, which is 5s squared, which is 25s squared. If I divide by 5, I get q squared is 5s squared, which means 5 divides q. And now I have a contradiction because I have 5 divides q and 5 divides r, but r and q have no common factor. They're relatively prime. So that's a contradiction. So the golden mean is an irrational number. Any questions about this? This is
Absolutely. Yes, yes, thank you. Um, First, if you have, let's just say a linear equation, so it will be both, it could be both rational and algebraic.
the solution of a linear equation. Well,
Yes.
first of all, so you can't talk about, so we're talking about numbers that are rational or algebraic or transcendental. So every rational number is an algebraic number, right? In fact, in this little picture, you see here the rationals contained in the algebraic numbers. Every rational is algebraic, but not every algebraic is rational. I just proved that the golden mean, root 5 minus 1 over 2, is irrational. It's not rational, but I'm about to show that it's algebraic.
Where did the when you got square root of 5 equals 1 plus 2p over q, right?
Yeah,
And
2p
then
over q,
yeah, so then let me see.
which is 2p plus q over q.
Yeah, so how where did this r over q come from?
Oh, so this is, I'm just saying, let r equal 2p plus q, just so simplify the notation.
Oh, okay.
2p plus q is an integer because p and q are integers, so that r be equal 2p plus q. So I have the square root of 5 is this fraction, r over q. And I can reduce it to lowest term, so I can assume that r and q have no common factor. So what I just showed is that gamma is not rational. It's an irrational number. But an irrational number could be algebraic or it could be transcendental. So the next step is to show that gamma, which is √5 minus 1 over 2, is algebraic. So that means I have to find a polynomial with integer coefficients for which gamma is a root. So if I take gamma, let's see, 2 gamma is √5 minus 1. So √5, so 2 gamma plus 1 is square root of 5. I'm just doing, baby operations here. I have gamma is √5 minus 1 over 2, multiplied by 2. Take the 1 from the right-hand side to the left-hand side. Now I have this, square both sides. I get that 2 gamma plus 1 squared is √5 squared. Because if I square √5, I get 5. And if I square 2 gamma plus 1, I get 4 gamma squared plus 4 gamma plus 1. So this equals this. So if I bring this from the right to the left, I get 4 gamma squared plus gamma plus 4 gamma minus 4 is 0. If I want to simplify, I can divide by 4. Gamma squared plus gamma minus 1 is 0. What does this say? Gamma is a root or a solution of the quadratic equation, of the quadratic polynomial, x squared plus x minus 1 equals 0. Because this says if I let x equal gamma, I get 0. So therefore, gamma is algebraic.
Professor,
Yeah.
may we go over problem 16?
All right. Sure. But any questions about this before we leave it?
Did you finish the C, define as zero, non-zero? But that's
Yeah. Here's the polynomial. It's quadratic, as it turns out. The coefficients are integers. 1 times x squared plus 1 times x plus minus 1. So this is the polynomial for which gamma is a root.
copy.
Okay. Problem 16. So in problem 16, you choose integers k and n, positive integers, k at most n, and we want to prove that the binomial coefficient n choose k can be written as n minus 1 choose k plus n minus 1 choose k minus 1. And just to provide some emotional support that this makes sense, let's just look at some examples. Suppose we take n equal 4 and k equal 2. So let's recall there are several ways to write a binomial coefficient, and which are equivalent. So n choose k, this binomial coefficient, we can write that as a fraction. The denominator is k factorial, which means the product of the integers from 1 to k. So it's a product of k factors. And the numerator is also a product of k factors, but you start with n and you go down by 1 until you have a total of k numbers in the numerator. So the last number you get will be n minus k plus 1. So that's one way to write the binomial coefficient n choose k. Or you could write this as, see here we have n minus 1 down to n minus k plus 1 over k factorial. What's the next number? The next number would be n minus k. And if we add in the numerator all the numbers from n minus, the product of all the numbers from n minus k down to 1, that's n minus k factorial. And then in the numerator, you have all the numbers from 1 to n. So you can also write this as n factorial over k factorial times n minus k factorial. So this is a bit easier formula to use usually, but this is a symmetric formula. And there's another way, there's another combinatorial interpretation of this. This is the number of k element subsets of a set with n elements. Okay. Let's just stick with this formula right here. So what is 4 choose 2? It's going to be 4 times 3 over 2 times 1. That's 12 over 2, that's 6. What is n minus 1 choose k? So if n is 4, n minus 1 is 3. So 3 choose 2 is 3 times 2 over 2 times 1. That's 6 over 2. That's equal to 3. If n is 4 and k is 2, n minus 1 is 3 and k is 1. 3 choose 1 is 3 over 1. Sorry, n minus 1 is 3. K, right, it's 3. Let's see, something here isn't right. 4 choose 3. 4 choose 2. That's 6. 3 choose 2 is 3 times 2 over 2 times 1. Is 3. Oh, yeah, this is all fine. 3, this is 3. So you'll notice 6 is 3 plus 3. That is 4 choose 2 is 3 choose 2 plus 3 choose 1. That's just an example of what we're trying to prove. Now let's look at another example. Suppose we take n equal 5 and k equal 3. So what is 5 choose 3? Is 5 times 4 times 3 over 3 times 2 times 1. This is 20, this is 60 over 6, that's 10.
Thank you.
So stop me if I'm going too fast. This is just arithmetic, but you have to follow the arithmetic. This is the binomial coefficient 5 choose 3. We have
How
to,
come? I'm
yeah,
sorry.
go ahead.
How come they didn't have the rest 5, 4, 3, and you didn't go down? You just stopped at 3.
because I'm using, this is the definition of the binomial coefficient. N choose k, you have k numbers in the denominator, the product of the numbers from k down to 1, and you also have k numbers in the numerator starting from n and going down. Well, you don't go down to 1, you go down to n minus k plus 1. So you have k numbers here and k numbers here. If you want to go down to 1 in the numerator, then you use this second formula where there are two different factors in the denominator. But that's our definition of the binomial coefficient. It's equal to this. There are many equivalent ways to write it. But if you have a 3 in the bottom of your binomial coefficient, there are going to be 3 numbers in the top starting with 5. 5, 4, 3. The 3 numbers, you stop. That's the definition.
Got it.
And what we want to prove is that 5 choose 3 is 4 choose 3 plus 4 choose 2, right? That's what in the case when n is 5 and k is 3, this is what we want to show. So 5 choose 3 is 10. What is 4 choose 3? 4, 3, 2 over 3, 2, 1. That's 4. What is 4 choose 2? 4 times 3 over 2 times 1, that's 6. So, and it is true that 10 equals 4 plus 6. So these are just examples of what it is we're trying to prove. And to prove the result in general requires some facility with algebra, I guess. Let's see. So suppose we have n minus 1 choose k plus n minus 1 choose k minus 1. What is that? So in the first fraction, we have a k factorial in the denominator. And in the numerator, we have k numbers starting with n minus 1 and going down. N minus 1, n minus 2, n minus k plus 1, down to n minus k. So you have k numbers here in the numerator. And you can see 1, 2 up to k there. N minus 1 to n minus k. That's n choose k. And this k minus 1 is n minus 1 choose k minus 1. You have a k minus 1 in the denominator, k minus 1 factorial. And then you have k minus 1 number starting with 1. So you have n minus 1, n minus 2, down to n minus k minus 1, which is, this is dot, 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 n minus k plus 1. And k factorial is the same. This is the product of all the numbers up to k. This is the same as k minus 1 factorial times k, right? K factorial is 1 times 2 times 3, k minus 1 times k. If I were to bracket it like this is just k minus 1 factorial times k. So I'm adding these two fractions. And I can factor something out of them. So each of them has a k minus 1 factorial in the denominator. And in the numerator, I have this times n minus k. And here, just this. So I could factor out this bit, n minus 1, n minus 2, down to n minus k plus 1. If I factor that out from the first term, I'm left with n minus k over k. Plus 1. I'm factoring this out. And n minus k over k plus 1, if you add fractions, this is just n over k. So I have this times n over k. So I have n times n minus 1 down to n minus k plus 1 over k times k minus 1 factorial, which is the same as k factorial. And if you look and you see this is exactly the definition of the binomial coefficient and choose k. So, I mean, this is just, I don't know what mathematics you want to call this. You can call it high school algebra, but sort of complicated high school algebra. You're not using calculus, you're not using vector spaces or linear algebra or group theory or anything. No differential equations. This is just algebra. It's old-fashioned high school algebra, not abstract algebra.
Can you name the high school this is in, please?
That's what I said. It's you won't find this in a high school, but it's high school algebra, but very complicated. You know, it's just like some problems are harder than others. Some are, you know, whatever. So it's not that you would expect a high school student to do this, but there's nothing that's used here that you did not learn in high school, right? I mean, again, we didn't use trig functions. There's no sine or cosine, no derivatives, no integrals, no differential equations, no vector spaces, no, right? I mean, what does this use? Well, technical ability at a very high level, perhaps, but not, anyway. But that's the proof, right? So it's what in mathematics one might call technically elementary. Doesn't mean it's easy. It just doesn't use more sophisticated concepts. Anyway, that's problem 16.
You said what problem is this? 10 or 16?
I'm sorry, I didn't hear what you said.
What problem is this one?
16.
Okay. Can we do problem 22?
Yep. Just 1 second. I'm sorry. Which question did you ask about? Did you say problem 22?
Yeah, she said 22.
Okay.
Yeah.
So problem 22, we have the polynomial f of x, which is 1 over 24, product I goes from 1 to 4, x minus I. So this means 1 over 24. And what this symbol means is x minus 1, x minus 2, x minus 3, x minus 4. And I want to put it into a form where the factors are like 1 minus x over something. So what is this? So you can notice, I guess, that 1 times 2 times 3 times 4 is 24. So this is 1 over 1 times 2 times 3 times 4 times x minus 1, x minus 2, x minus 3, x minus 4. Or I could write this, I could put this over 1 times 2 times 3 times 4. That's the same thing. Which is the same as x minus 1 over 1 times x minus 2 over 2 times x minus 3 over 3 times x minus 4 over 4. Which is the same as x minus 1, x over 2 minus 1, x over 3 minus 1, x over 4 minus 1. And now, if I change x minus 1 to 1 minus x, I'm multiplying by minus 1. And if I change this in the opposite order, 1 minus x over 2, 1 minus x over 3, 1 minus x over 4, I'm just multiplying this by minus 1 times minus 1, minus 1, minus 1, minus 1 to the 4th power. That's just plus 1. And I'm done. So this is like a equal 1, b equal 2, c equal 3, d equal 4. It's exactly of the form we want.
What would you call this topic?
Mathematics?
No, this specific
High
question.
school algebra?
No, this specific question. What topic in math would it fall under?
I don't know. Theory of equations? Polynomials? I mean, this was part of Euler's proof that the sum of the reciprocals of the squares was pi squared over 6. This came up in proving summation 1 over n squared, n goes from 1 to infinity, is pi squared over 6. Right? That was a great theorem of Euler. So in that proof, we use this way of representing a polynomial.
Oh, okay.
Right? But this is much, much simpler than proving this whole theorem.
Professor, you did A equals 1, B equals 2, C is 1,
3.
3, and 4. Okay.
The denominators of the x's are 1, in this case, 1, 2, 3, and 4.
Professor, one question.
Yep.
So for the second to last part, what allowed you to switch the signs
From
of
here to here?
mhm. Yeah,
Okay.
what allowed you to switch?
Okay. So I have x minus 1, x over 2 minus 1, x over 3 minus 1, x over 4 minus 1. So you'll notice that x minus 1 is minus 1 minus x, right? So x minus 1 is minus 1 minus x. Right? I mean, do you believe that? X minus
Uh,
1, x minus 1 is minus 1 minus x. Right? So you just minus 1 plus x. Is that okay?
I get it now. Thank you,
Just
thank you.
minus 9. And then this is minus 1
Right, then
minus x over 2.
you
And this is
continually do
minus
that.
1 minus x over 3. And this is minus 1 minus x over 4. And I have minus times minus times minus times minus is plus.
Okay, thank you. Can we go over problem 27?
Problem 27. Okay. So in problem 27, P is a prime number. And in part A, we take an integer K between 1 and P minus 1. So the important thing is that the binomial coefficients, n choose K, is always a positive integer. That is, whatever is in the denominator factors into what's in the numerator. So that's the starting point of this. So if you take P choose K, what is that? The denominator is K factorial. 1 times 2 times the product of all the numbers up to K. And the numerator is K numbers starting with P and going down. P, P minus 1, P minus 2, P minus K plus 1. Okay? That's the definition of this binomial coefficient. And what you see is that I have a P in the numerator. But I also know, since this turns out to be an integer, that every one of these numbers divides into something in the numerator. But K is less than P. So there's no P in the denominator. There's no number P down here. So nothing cancels the P in the numerator. We have this P here. There's nothing to cancel it. Here, like take an example. Suppose I take P equals 7, K equals 4. So 7 choose 4. I have 7, 6, 5, 4. And in the denominator, 4, 3, 2, 1. Now everything gets canceled that's in the denominator, but there's no 7 in the denominator. No, there's nothing to cancel the 7. So like 4 cancels 4, and 3 times 2 is 6, cancels the 6. This is 7 times 5 or 35, but this is divisible by 7. And in general, if you write the binomial coefficient P choose K, where P is a prime, K is less than P. It's the most P minus 1. So you're not going to get any P in the denominator. Nothing cancels this P. So this is going to be an integer divisible by P. And that's what we were supposed to prove. P divides the binomial coefficient. P divides P choose K. And you can just look at some examples, some more examples, just to convince yourself it's true. Suppose I take 11, choose 7, where 11 is a prime. 11, 10, 9, 8, 7, 6, 5. There are 7 numbers there. 7, 6, 5, 4, 3, 2, 1. I claim this is going to be divisible by 11. Well, there's no 11 in the denominator to cancel this 11. So let's say here I have 7, 6, 5. Here's 7, 6, 5. That cancels. I have 4 times 2 is 8, cancels the 8. 3 goes into the 9. That gives me 3. So this is 11 times 10 times 3, which is 11 times 30. It's divisible by 11. It's 330. This is divisible by 11. Okay. Here I have a prime. There's no prime in the denominator to cancel it, so the integer you're left over with is a multiple of the prime.
When you say there's no prime, you mean after the cancellations?
Before or after. I mean, here, there's no P in the denominator. If I look at P choose K, this binomial coefficient, this is the formula for what this number is. You see a P in the numerator, but there's no P in the denominator. P is a prime. So these are numbers less than P. K is less than P. It's at most P minus 1. So there's no P down here. There's nothing to cancel the P when you do your cancellations. Because P is a prime. It's not a product of 2 smaller numbers. There's no P in the denominator to cancel that.
Professor, did you do part B and C?
Yes. So this is a proof that takes several pages in the text. So this is in Euler's work on number theory. This is in chapter 10 on pages 226 to 228. So we want to prove so this is part B. We want to prove that a plus 1 to the p minus a to the p minus 1 is always divisible by p. P is a prime. So you have to know the binomial theorem. Not Newton's binomial theorem, but the baby binomial theorem must know the binomial theorem. The binomial theorem says that a plus 1 to the p when you expand this, is a to the p plus the binomial coefficient p choose 1, a to the p minus 1, the binomial coefficient p choose 2, a to the p minus 2, the binomial coefficient p choose 3, a to the p minus 3, and you just keep going down, you get finally p minus 1 times a plus 1. That's the binomial theorem. And if you look at this, in all of these terms, you have an expression of the form p choose k, a to the p minus k, where k is between 1 and p minus 1. And what we proved in part A is that each of these binomial coefficients is divisible by p. So if this, and everything in sight is an integer, right? The a's are integers. And the binomial coefficients are integers. So if this is a multiple of p and you multiply it by something else, you still have a multiple of p. So these are all multiples of p. So everything in here, this is some multiple of p. So if I take a plus 1 to the p minus a to the p minus 1, that's all this. That's a multiple of p. Or this is something which is divisible by p, which means the same thing. So if you take a plus 1 to the p and expand it by the binomial theorem, you get this result. If you take on the right hand side, the a to the p and the 1, and you move them to the right, you're left with all this. And every one of these numbers is divisible by p, so the sum is divisible by p. That's the proof for part B. Questions about this?
I'm assuming we learned this in middle school, but
No, Oh, sorry. Yeah, go ahead. Learned what?
This binomial theorem
No,
algebra.
you didn't learn it in middle school.
Okay.
You might not have learned it until this course, though. It actually comes up in Calc 1 because you use this when you're learning how to differentiate. Like, remember you learn how like the derivative of x to the n is n x to the n minus 1. Remember that?
Mm-hmm.
So the derivative of x to the n is the limit of x plus h to the n minus x to the n over h as h goes to 0, right? That's the definition of the derivative. This is the difference quotient. How do you compute that? You say that x plus h to the n is x to the n plus binomial coefficient n choose 1, x to the n minus 1h, binomial coefficient n choose 2, x to the n minus 2h squared, and so forth, right? That is, you have the way you prove the derivative of x to the n is n x to the n minus 1. You have to evaluate this difference quotient, and you do that by using the binomial coefficient here. Now, it may be your teacher skipped this and just told you the formula, or maybe your teacher did this but didn't expect you to know it or follow it. But this is in all the books. If you look at your calculus book, you'll find exactly this. This is the basic way to compute what is the fundamental differentiation formula. So, but it may be that this is the first course where you've had to learn the binomial theorem. But I assume if you're taking this class, you're like either a math major or in math ed and going to teach high school math. And binomial theorem is something you should know. And
How many?
if you're seeing it for the first time, that's okay. But it's just something that's, there's a lot of basic mathematics. There's so much basic mathematics, no one knows it all. But this is just something that's, really is very basic. And it goes back a couple of thousand years. Yeah, it's been around for a long time. In Babylonia, in India, in China, 2,000 years ago, people knew this.
And how many different versions do they have of this binomial theorem?
Well, one. This is it. I mean, you can write equivalent versions, I guess, but it's just like the binomial theorem involves the binomial coefficients. There are many different formulas for the binomial coefficients. They all give you the same number. They're equivalent formulas, but there's only one binomial theorem.
Oh, that's what I was talking about, the coefficient. Because every time I look it up online, it's always a different variation of it.
Well, usually they're just two, the two that I showed you at the beginning. So let's see. Let me see where it is. Yeah. So there's this there's this definition of the binomial coefficient where you take n choose k, you have the product of n numbers in the numerator, sorry, k numbers in the numerator and k in the denominator. In the denominator, it's k factorial. In the numerator, it's n, and then going down by 1. Or there's a more symmetric form, which is just use factorials, n factorial over k factorial times n minus k factorial. I mean, they give you the same number. And then there's also a combinatorial definition that doesn't involve a formula. It says if you have a set with n different elements and you want to choose k of them and get a subset with k elements, the number of different k element subsets of a set with n elements is always equal to the binomial coefficient. I mean, these are the basic ones. And I doubt if you're looking for the, if you look up what is the binomial coefficient, you probably don't see anything else. Now, what we learned in the chapter on Newton was Newton's binomial theorem, which was a great generalization of this basic one. So in the text in chapter 7, on page 165, there's Newton's binomial theorem when, so in the simplest binomial theorem, you have x plus h raised to the power n, where n is a positive integer. And Newton's generalization is to define this when n is not necessarily an integer and could be positive or negative. So you could have x plus h to the power, square root of 2 or something. That's Newton's binomial theorem. So we spent a lot of time with that when we were studying Newton's work. A large part of chapter 7 is on Newton's binomial theorem, and they spend about 10 pages talking about it.
Professor,
Mm-hmm.
can we do problem 30?
Just 1 second. I'm sorry, which question did you ask about?
She said 30.
30, yeah.
Number 30. Okay. So n is the set of positive integers. And n squared is the set of ordered pairs of positive integers. And we want to prove that the number of positive integers equals the number of integers. So we must show there exists a function f from n squared to n that is a one-to-one correspondence. That means one-to-one and onto.
Question.
Right?
Does it matter the order? It does, right?
What do you mean
N2,
by the order?
when it says the function of n squared to n, does it matter if you flip the order around?
What is the order?
So
You mean a function from n to n squared?
yes, does it matter the order? Like if you put the function of n to n squared?
Or, okay, or it's the same thing. Or there exists a function that say g from n to n squared. That's a one-to-one correspondence. Either way.
I thought that the first one represents the domain, and then the second is a codomain. So
No, that's true, but this it doesn't matter. You have two sets. If there's a one-to-one correspondence between them, if the sets are A and B, it doesn't matter whether your function goes from A to B or from B to A.
but if
They're different
that,
functions. But if
oh,
there
but
exists a function, so note, we have sets A and B. So there exists a one-to-one correspondence F from A to B if and only if there exists a one-to-one correspondence G from B to A, right? If you have a one-to-one correspondence from A to B, then there's always a one-to-one correspondence from B to A. So it doesn't matter which you prove. In fact,
okay.
you just take G to be the inverse of B. So if this is the set A, and this is the set B, and you have a function f from A to B, and the element A gets sent to the element B equal f of A, you can define a function.
Oh, we can't see the paper. Sorry.
You can define a function G from B back to A, which sends B back to A. Okay. You can take G to be F inverse. There's a one-to-one correspondence always has an inverse. So if you have two sets and you want to show they're equivalent, that they have the same number of elements, you have to show there's a one-to-one correspondence from one of the sets to the other. It doesn't matter which one comes first and which one. It doesn't matter which is the domain and which is the codomain.
Oh, okay. And for it to be one-to-one, it has to be onto and
No. For it to be a one-to-one correspondence, it has to be one-to-one and onto.
oh, okay.
So, and I don't care which way you want to do the function. So let's say you have, here I'm going to have n squared. So it's just the positive, not the lattice points on the x and y axes, but just these points. And so on, right? They go on forever. So these are the lattice points. And I just have to find a function f. I just have to prove there exists a function f from n squared to n, which is a one-to-one correspondence. And what I said is one way you can do this, there are lots of ways to do it. One way is to look at the points on successive diagonals. So and you see every point, no matter what point you pick, no lattice point, it's on some diagonal. So as you go along these diagonals, you're going to hit every point. So our function, we can say, well, we'll send this to the number 1. So f of 1, 1 will be 1. This is 2, 1, and this is 1, 2. So maybe f of 2, 1 is 2, and f of 1, 2 is 3. I'm sending this to 2 and this to 3. And I'm going to send this to 4, 5, and 6, and so on. And I just enumerate the points that way. Eventually, I assign a number to every lattice point, and it's a one-to-one correspondence. I could actually give a formula for this. I'm not going to, but I can actually give a formula for this. But this is a one-to-one correspondence.
So when you go from on the second one, when you go to order pair 2 to 1, how do you get 2?
Well, I'm sending this lattice point to number 1, this lattice point to number 2, this lattice point to number 3, this to 4, this to 5, this to 6, this to 7, 8, 9, 10. This will go to 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I can just enumerate the lattice points like that. And that's one way to do it. If you don't like diagonals, you could do it a different way. I mean, there are infinitely many different ways to do it. You could say, okay, I'll start with this, and then I'll take like successive squares. I'll go like, this will be 1, this will go to 2, this will go to 3, this will go to 4. Then I look at this next sort of right angle. This will go to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13. I can just take these successive right angles, and any point in any lattice point is going to be on one of these right angles, and I can enumerate the points that way. So I'm not giving you the formula. I'm not giving you the function with a formula. but I'm giving you the function. I'm proving there exists such a function.
So that would be how you write the answer.
Yeah, but it takes a paragraph description. You have to write in sentences what I'm saying. You can enumerate the lattice points by observing that every lattice point in the first quadrant lies on one of these diagonals. And as you enumerate the point from one diagonal set of points to the next, you hit every lattice point, and every lattice point is counted. I mean, if this were a more advanced class, I could actually work out a formula for this, but it takes an hour or two of work. But to show two sets have the same number of elements means to show that there exists a one-to-one correspondence between them. It doesn't mean you have to write down the one-to-one correspondence by a formula. So you have to prove the existence of such a function. You don't have to describe how it operates by a formula.
Professor, can we go back to um problem 7? Computing the triangle whose side length are 3, 5, and 7.
Problem number 7,
Yes.
to state Heron's formula,
No, the second part.
you use it to compute the area of the triangle.
Yeah.
Okay, so you have a triangle with sides A, B, and C. The perimeter is A plus B plus C, and half the perimeter, or the semi-perimeter, is a number we call S. And the Heron's formula says the area of the triangle is S minus A, S minus B, S minus C. So in problem 7, A is 3, B is 5, C is 7. A plus B plus C is 15. Divided by 2, you get 15 over 2. That's S. So this is the square root of 15 over 2. 15 over 2 minus 3. 15 over 2 minus 5. 15 over 2 minus 7. It's the square root of 15 over 2, 9 over 2, 5 over 2, 1 over 2, right? So This is the square root of 15 is 3 times 5. So this is 3 times 9 times 25 over 16. So if I take the square root of 9 is 3, square root of 25 is 5, square root of 16 is 4. So 3 times 5, I have 15 over 4 times the square root of 3, if I did this correctly. The sides are 3, 5, and 7. That adds up to 15. Half of that is 15 over 2. So this is 15 over 2 minus 9. Is that right? So 15 over 2 minus 3, which is 6 halves. So that's 9 halves, 5 halves, 1 half. Yeah, this looks good. So that's Howard's formula.
Is that 3 times 9 times? What did you write at the bottom?
So I'm sorry, I can't understand what you're saying. Could you repeat what you said, please?
The bottom one, what did you write? 3 times 9 times. Is
25.
that 25?
Yeah.
Oh,
I'm just multiplying this out.
okay.
5 times 5 is 25. 3, 9. I mean, just to make it easier to take the square root. 3 times 5 over 4 times square root of 3.
Can we do 11? Find the depressed cubic. Change from the cubic.
So we have 2x cubed minus 18x squared plus 8x plus 2. Okay. So let's see, you have the book, and the depressed cubic comes up in solving the cubic equation. So let's do it the easiest way. Let's just see what the book tells us to do. So the cubic equation is Cardano's solution of the cubic. And let's see. I mean, I can do it in two ways, but if we have ax cubed plus bx squared plus cx plus d, this is the same as, let's see, what's the nicest way to do that? No, let me just do it easily. So this is going to be the same as 2, factor out of 2, x cubed minus 9x squared plus 4x plus 1. And if I let x be equal to y plus, what should I let it be? the y plus 3. Let's see what happens. So, or sorry. So let me make it quick. Here I have this polynomial. So the roots of this are exactly the same as the roots that I would get by dividing by 2. So if I divide by 2, I'm left with this. So the first step would be to observe that I want to depress the cubic x cubed minus 9x squared plus 4x plus 1. And if I let x equal y plus 3, what happens? I get y plus 3 cubed minus 9, y plus 3 squared plus 4 times y plus 3 plus 1. So then I have to expand this using, again, the binomial theorem. How do you expand this? You get y cubed plus 3 times 3y squared plus 3 times 3 squared times y plus 3 cubed. That's this. This is minus 9 times y squared plus 6y plus 9 plus 4y plus 12 plus 1. So here I have y cubed. Here I have 9y squared, and here I have minus 9y squared. So they cancel. And then I have 27y plus 27 minus 54y minus 81 plus 4y plus 13. This is y cubed. 27y minus 54y is minus 27y, plus 4y is minus 23y. 27 minus 81 is minus 54, plus 13 is minus 41. So if I did the arithmetic correctly, this is the depressed cubic that you get. In general, if you have, forget the, if you divide by the leading coefficient, so you have x cubed plus ax squared plus bx plus c, you let y equal x, you let x equal y minus a over 3.
Is it 3b?
Well, no. If it's monic, so it's exactly this. If it were ax cubed plus bx squared, it would be b over 3a. And the first step should be to divide by the leading coefficient. So you get an equivalent polynomial where the leading coefficient is 1. So if it's cubic, you can write it as x cubed plus ax squared plus bx plus c. And then you let x equal y minus a over 3. So in this case, a is minus 9. So minus a over 3 is 3. So that's why I was substituting x equal y plus 3.
For the final, if we don't finish in 2 hours, can we have more time?
No,
Thanks.
no, it's a 2-hour final. That's standard of Lehman. So I'll have to make the questions easy so they don't take a lot of time. Okay, so that's it for today. I'm available tonight on Zoom at 7. I'm going to try to be available tomorrow at 7, but I have to be at the CUNY Graduate Center, and I'm not sure when I'll get home. So if I'm home by 7, I will definitely log on to Zoom. And I'll also set up a time on Sunday in the afternoon, I think, if you have any last minute questions before the exam. Okay, that's it. See you live and in person on Monday morning, bright and early. Bye.